The Laplace transform of a periodic function is as shown on your screen in the form of a theorem. If f of t is a periodic function with the period t, then the Laplace transform of f of t is given to be 1 divided by 1 minus e to power minus st. This t, you should be very careful about it. This t is not that small t, it is the period t, capital T. Integration from 0 to t, again that capital T, which is the period of that function, e to power minus st f of t dt. So let us prove this. The proof goes as the Laplace transform of f of t. We will just consider the basic definition of Laplace transform, that is integration from 0 to infinity e to power minus st f of t dt. By this time I think everyone remembers this very well. Okay, now I'll change the variable from t to u. Just I am rewriting it in terms of u. There is no change in the definition, just I am replacing every t by u, so that okay. Now since the function has been defined in from 0 to t, it is defined to be f of u. From t to 2t, it is defined to be f of u. Similarly, from 2t to 3t, it is defined to be the same. So based on that period, I will just split my interval from 0 to infinity. Just see, integration from 0 to t, e to power minus su, f of u du, plus integration t to 2t, e to power minus su, f of u du, plus integration 2t to 3t, e to power minus su, f of u du, plus so on. Now I can rewrite this as in a simplest form, that is summation from for n going from 0 to infinity, integration from n into t to n plus 1 into t, n plus 1 into t, e to power minus su, f of u du. That is, all these I can write it in summation form like this. Is it not? Just check it. Okay, now what I will do, I'll put u is equals to, just see that in this I'll put u is equals to t plus n into t plus n into t, so that du is equals to dt, because however this n and t both are constants as far as this u and t are concerned. This n is a natural number, okay, for a particular interval, for a particular time it will be n 1, 2 or 3, and this period is fixed for any this function, okay. So du is equals to dt. Now when this u is equals to n into t, that is the lower limit, you get t is equals to 0, and when u is equals to n plus 1 into t, I shall write it here. When u is equals to n plus 1 into t, you get capital small t as, just see, n into t will get cancelled, small t will be equal to capital T. So let us do these substitutions in this expression. So therefore the Laplace transform of the periodic function f of t is defined to be, we have obtained it as summation n going from 0 to infinity, integration from 0 to t now, just see that, e to the power minus s, in place of u you are writing t plus n into t, is it? Now this into f of u you are writing t plus n into t, and du is equal to dt. I am replacing every u by that defined thing, okay. Now this is again equal to summation n going from 0 to infinity. Now from this complete interval, from this particular integral, you see that the integration only goes for small t, not for the capital T term, because these two are constants. So I can write this as integration from 0 to t, capital T, e to power minus st into e to power minus sn capital T, now since f of t is periodic, f of t plus n into t is f of t only, yes or no? So you get this as f of t dt, is it? I hope it is seen there. Now further, this is equal to summation n going from 0 to infinity. Now this term, it has nothing to do with the integral sign, get it outside. Integration from 0 to t, e to power minus st, f of t dt. Okay, now keep this aside. Okay, this is half part of your theorem. Just see that this is there here. This we have derived now. Only this part we have to do. Okay, now to do that part, just see. It is summation n going from 0 to infinity. Let us consider this. Summation n going from 0 to infinity. I hope it is seen there. Yes. E to power minus snt Now for n going from 0 to infinity, let us expand this. So it is nothing but 1. For n is equal to 0, it becomes e to the power 0, which is 1, plus e to the power minus st plus e to the power minus 2 st. For n is equal to 2. For 3, it will be minus 3 st plus so on, right? Now what do you think about this? Is this not a geometric series? This is geometric series with common ratio r is equal to e to the power minus st. Is it not? Yes, and its sum up to infinity we are considering. What is the sum up to infinity for the geometric series for r less than 1? Is it not s less than 1? Because it is r is equal to 1 divided by e to the power st over here. Now s is positive and even this. Yes, even this. So 1 divided by this gives you what? A number less than 1 or no? Whenever r is less than 1, what is the sum up to infinity for this geometric series? Yes, sum up to infinity for this Sn, it is 1 divided by 1 minus r, or sorry, a divided by 1 minus r. R is the common ratio, a is the first term. Is it not? So here a is 1. So the sum up to infinity is 1 divided by 1 minus e to the power, r value is e to the power minus st. Yes? This is sum up to infinity. Now we have to replace this summation into e to the power summation of e to the power minus st to by this term. Is it not? So therefore, we get this as, I'll write it in a simplified form over here. I hope this point is clear to everyone. The sum up to infinity for geometric series for r less than 1, you have this formula with you. Okay, Sn, a divided by 1 minus r. Okay, sum up to infinity. I should write not Sn over here, sum up to infinity, S infinity. So similarly, you get, by referring that, you get this sum up to infinity like this. Now let us substitute that in our expression over here. That is, I'll continue it here only. That is equal to, now this term you have to replace it by 1 divided by 1 minus e to the power minus st. So it will be 1 divided by 1 minus e to the power minus st, integration from 0 to t, e to the power minus st, f of t dt, which is the required Laplace transform of the periodic function. Continue in my next class with the problems. Thank you.